go ahead and get started. So welcome to EGGN 281. That's the Introduction to Electrical Circuits. Just want to make sure everybody's where they think they're supposed to be. So that's what this course will be covering. What I'd like to do here initially is go through some of the aspects of the syllabus with you, just to point out the administrative aspects and how you'll be evaluated, that type of thing. Okay, this semester there are 6 sections of this course. I'll be teaching 2 of those sections, and then the other professors, Dr. Dave, Dr. Smoes, and Dr. Ahmed. So it's nice from the perspective, the class sizes are a little smaller this time, so I'm hopeful that will encourage interaction. So please feel free to ask questions if there's something that's unclear. Happy to stop and try to elaborate on particular points. You'll notice all the instructor contact information is provided. And I'll just point out I'm much more likely to respond in a timely fashion if you email me. I have a bad habit. I ignore my phone message box. So you're welcome to leave that, but I think you'll get a better response if you email me. All right, the prereq for this course is Physics 2. So if the registrar is doing their job, you weren't able to enroll without completing Physics 2. I'll talk a little bit more about that course in a little bit. The course objectives and the course description are provided. I would encourage you to look at that. Probably the objectives, that is most worthwhile at the end of the semester to see if you believe that we really accomplished the objectives that we set forth. Okay, the Blackboard, we will be using that to disseminate information. So I do want to emphasize it's important that you check that on a regular basis. Homework solutions, review material for exams, old exams, that type of thing will all be posted on Blackboard, as well as your grades will be posted there. So that gives you a way of making sure that we've recorded the correct scores for the various homework and exams. All right, comments on the textbook. I do want to emphasize that you are likely to see 2 versions, so I just want to explain. This is the full version of the electrical circuits text. It is 18 chapters worth. We will only cover the first 9, and so most of you will probably find the custom text a little more economical approach. In other words, it just essentially gives the 9 chapters that we will actually cover. I do want to emphasize, if you are an electrical major, you might consider getting the full text, because the follow-up course, Circuits 2, will then cover the remaining 9 chapters. So that's an option. The other thing I want to stress is when you purchase this text, you will need an access code to Mastering Engineering. We intend to use that platform for online homework assignments, so you will need to purchase that access code. Now, it's my belief most of you probably have gone through statics, so you are familiar with the Mastering Engineering platform, so that shouldn't be too new of a process, just a continuation with that type of platform. All right, the homework. I want to emphasize that each homework assignment will consist of 2 parts. There will be an online portion. So in fact, if you have signed on to Mastering Engineering, that first assignment became active at 8 a.m. this morning. There are 2 parts to that. Just a brief introduction, just to emphasize some of the logistics or administrative aspects of Mastering Engineering, and then the first circuits assignment. And then also, we will be assigning typically 4 to 5 written problems each week. It's very important, particularly as you prepare for the exams, that you get familiar with the process of laying out circuit analysis in a very systematic fashion. So I don't think if we just essentially assign only online assignments that you get practice in that type of thing that will help you prepare for the exams. I'll talk a little bit more about the course outline here momentarily, but I do want to emphasize that homework assignments are always due on Wednesday. The written assignment, please get in the habit when you come into class, just put those at probably right on the desk up by the podium. And then the online assignment is due 5 p.m. that same day. So always homework is going to be due on Wednesdays. That being said, the first assignment is then due a week from Wednesday, so that's January 16th. Okay, it mentions short quizzes, the possibility of that. I have to be honest, in here there is so much material to cover that last semester I only gave one quiz. I imagine that's pretty representative of what will happen this semester as well. So I will announce quizzes in advance. So it's something that I deem to be extremely important if I dedicate class time to quizzes. So I will let you know in advance. All right, more comments on the syllabus about mastering engineering. So I'll just call your attention to what you need to do to register for this class. And then the third page talks about how your grade is established. So you'll notice both the online homework and the written homework are worth 10%. We have instructor discretion and short quizzes for 5%. And then this semester we have 2 exams during the semester and a final. So each one of those exams is worth 25%. So as you can imagine, a lot riding on those exams, so very important to make sure and prepare for those. We will be using the plus and minus grading scheme in here, so the grade allocation is laid out in that table. One thing I want to mention, there's a heading titled attendance, so I want to give you my perspective here. Now in a smaller class, I will certainly miss you if you're gone. I'm not going to take attendance, but here's my point. Electrical engineering is an extremely abstract subject. You're going to need my help, I believe, to really master the material. Reading the textbook will certainly be important, but I think it's very important to make attendance a priority. I've had people mention to me if they miss a class, they have no idea what I'm talking about. This class moves at a very high rate of speed, so you would be surprised how much material you may miss if you are gone for a lecture. So again, that's my plea is I will promise not to waste your time in here. I know you're all very skilled readers. I don't plan to regurgitate or review what's in the textbook. My intent is to supplement the material, to give you other perspectives to help come to grips with trying to visualize the invisible, which is what we're asking you to do largely in the realm of electrical engineering. Okay, the attendance policy, or not the attendance, but the academic dishonesty policy is just published here. That's a request the administration asks us essentially to adhere to. I do want to emphasize one of my concerns is I'm very well aware that solution manuals are readily available to this material. That being said, if you just go through the process of copying down a solution, that does you absolutely no good. And my graders are pretty astute at recognizing that. So just be aware that the possibility exists that I might ask you to explain that material to me if I just see the material directly copied from a solution. So again, homework is to help you master the material. Just copying it blindly does you absolutely no good whatsoever. All right, so with that, I do want to mention on the remaining 3 pages, the semester is laid out day by day. So today will be beyond the introduction of the material. We'll look at some fundamental circuit principles. The reading, unfortunately, you're already behind. Ideally, you would have read the first 18 pages of the text. If you can read the material in advance of the lecture, I think it helps solidify that material. And then you'll notice on the 16th of January, the homework assignment, that's when that is due. So there is, once again, the online component and then the written component. And then beyond that, the exams are described. We are giving exams since there are 6 sections. We'll give those during the common exam time frame. So those are laid out as described. So with that, are there any questions about the syllabus, the administrative aspects of the course? All right. Did everybody get a copy of the syllabus? So as we begin this process together, I think there are 2 questions we should probably consider. So the first question, and I'll try to clarify this because this may strike you as a bit odd, but the first question I think we should consider is, why are you taking this course? Now, the reason I'm asking that question is, as I looked through the class list, I noticed that less than 10% of you in here are declaring electrical engineering as your specialty. And so what I interpret that to mean is, some point in your life, you decided to do something other than follow electrical engineering as your dream job or whatever. That might be when you were really young, you stuck a butter knife in a wall outlet or a set of keys. This spray of sparks, if that didn't terrify you enough, the adults yelling at you certainly did. Maybe it was later in life, physics 2, so it could be fairly recently. You decided that no way do you want to do anything electrical if physics 2 is a representation. So the point is, for some reason, the majority of you in here are non-electrical engineering majors. So let me return to my question. Why are you taking this course then? Exactly. That's the answer I would expect. It is required. In other words, your faculty, or the faculty that essentially administer your degree requirements, are stating that to get an undergraduate degree from the Colorado School of Mines, you must endure EGGN 281 Intro to Circuits. Now here's the important point. It's your faculty under which you're getting the degree that sets your degree requirements, not me. So if you are frustrated by having to sit here, I can't help you. You would have to address those problems to the faculty that you're directly getting the degree from. So here's another point. I am truly here to help you. I'm an ally in this process, and I hope you come to believe that as the semester goes by. I can help you get through this course, and hopefully in the end you will see why it's so important to have a basic understanding of electrical engineering. I certainly agree with your faculty that you need that. We live in an electrified world. Certainly, as an engineer, you have to have some basic understanding of electrical phenomena. So again, I certainly support that non-electrical students are required to take this class. Some other aspects where this course may become very useful. How many of you know of and plan to take the FE exam? Okay, so good. Hopefully by the end of the semester you'll all raise your hand when I ask that same question. The FE exam is the Fundamental of Engineering exam. It's the first step in becoming a professional registered engineer, And for a lot of you, that will certainly be a requirement to meet your professional goals. Another aspect, I can guarantee that you'll be working on multidisciplinary teams where you will likely be working with electrical engineering specialists. It's important to be able to at least have some idea what they're talking about and guide that process. So a lot of reasons you're here, so that's why you're taking the course, other than it's just a requirement for graduation. That being said, the second question if the faculty under which you study have decided that you need to take this course, it's probably important to ask yourself, what is electrical engineering? So anybody want to take an attempt or a stab at that particular question? Incidentally, as you probably know, electrical engineering is a huge, vast field of study. So it's a little challenging to break that down into a nice, concise definition. So here's what I would generally tell people if you're trying to grasp what electrical engineering involves. If it involves processing energy or information, it is likely going to fall under the classification of electrical engineering. So I will refer to that definition frequently throughout the semester. Might as well get that well ingrained right now. So I could spend the remaining class period just talking about energy and information, but I don't think that's really what we want to do. Let me just briefly mention some things that you should be well aware of that fall under those two headings. So in other words, what I would ask on a day-to-day basis, think about how much you depend on electrical phenomenon or electrical engineers to do their jobs so that things that you take for granted are working properly. So what's a good example under energy? Okay, I'll mention computers under the information, because processing, using ones and zero binary, so definitely you're all aware how much we depend on computers. From an energy perspective, we distribute, we generate, and we utilize power, electrical energy. So that's one thing looking there. So in terms of power, another aspect under energy would be electromagnetics, so the use of electrical and magnetic fields. And incidentally, I think it's important for you to know the perspective your instructor brings, so that the area that I work most closely with is the power aspect. That doesn't mean that I'm unable to really address the other aspects, but certainly that's my area of expertise. And then under information, you mentioned computers, so definitely excellent example. What are other examples of information processing? Think of all the communication tools we rely on, so cell phones, radios, television. There are certainly many examples in all the engineering disciplines that you represent here in this class of control systems. In other words, automated control systems is common in all the engineering disciplines. So control systems, signal processing, So that just gives you a sampling of some of the things we're describing, some of the areas that are essentially under the context or the heading of electrical engineering. All right, another thing to mention, it's reported that the IEEE, which some of you will recognize, that's the Institute of Electrical and Electronic Engineers. It's the Electrical Engineering Professional Society. It's reported to be the largest engineering society in the world, indicating just what a vast field of study this has become. Another question, how many of you are involved in the Professional Engineering Society that essentially represents your degree? That would be another thing by the end of the semester. I hope all of you raise your hand. That is such an excellent way to network, to make contacts, to get timely information about your field of study. They generally give you really good discounts as a student, so I'd encourage you to consider joining one of your, or whatever professional society is representing your degree. All right, so a little bit of discussion about the course. This course, as the title indicates, is an introduction to circuits. That means we have to spend the majority of time on circuit analysis and problem solving. The reason that's how we're going to focus our time is once you master the foundation of circuit analysis and problem solving, you have the foundation for any other aspect of electrical engineering that you might need to study. This course moves at a high rate of speed. I can't overemphasize that. We have a lot of material to cover, so it's very important that you don't fall behind. If I see students struggling, it's usually because they don't get that good foundation from the beginning. If you really focus on learning the circuit analysis techniques, what comes later in the semester should fall into place nicely. So I encourage you, get help, make sure that you get up to speed with the techniques we'll start with. All right, so any questions on that? So what I'd like to spend the remaining part of the day doing is just give a brief review of the electric circuit fundamentals. Okay, so if you go back to Physics 2, what hopefully you glean from that course is that electrical effects are attributed to separation of charge and charge and motion. So separation of charge you should recognize as voltage, charge and motion recognized as current. So again, all electrical effects are attributed to charge being separated or the movement of charge. So that's where we want to start, is just quickly looking at the following fundamental quantities: charge, voltage, current, and then power and energy. I just want to make sure as we get started that everybody's on the same page, that we essentially have the same understanding, the same perspective. So just a couple of quick things to review. Charge on an electron given as negative 1.602 times 10 to the negative 19th. Charge is measured in coulombs. And then charge on a proton. Okay, one thing I'll reference is the bipolar nature of charge. That's significant, and that gives a lot of initial problems with sign conventions. So as your instructor, anticipating where you might have problems, I'll try to focus on really getting a system in place where you don't have to worry about the signs and the directions, and that way you don't have to be concerned about that, and you'll let the circuit analysis take care of itself, so to speak. Okay, next, current. We mentioned that's the movement of charge, so current. Is described as the time rate of change of charge. So it gives us a good opportunity to just quickly review units of current, coulombs per second. And you hopefully recognize that by a more common representation, and what would that be? Yep, an ampere, or amp for short. All right, so this may seem like a funny thing to focus on, but again, recognizing some of the problems that people find pertaining to circuit analysis, I really want to emphasize the following. Charge is bipolar. That means if we're going to designate a current, to correctly and completely describe it, we have to indicate a magnitude and a direction. In other words, you can't give one without the other to fully and completely define that current. So let me just show you a couple of equally valid ways to present information about a current flowing in a particular segment of a circuit. All right, you might choose to indicate the direction of current from left to right and indicate that its magnitude is 10 amps, and it's equally correct to designate that same current flowing from right to left as negative 10 amps. So that may seem like I'm stating the obvious, but I'll come back to the significance of that as we get further into the circuit analysis. Next fundamental quantity, voltage. So I just want to emphasize here separation of charge. So it's the amount of work done per unit charge in separating. So we can designate that as WDQ. So here again, good opportunity to review units. So joules per coulomb. Or more commonly called a volt. Now you're going to notice there's a familiar theme here. Because charge is bipolar, that means that to correctly designate and specify a voltage, we have to show a polarity and a magnitude. So if I take a circuit element and want to present or represent voltage associated with the circuit element, a couple of equally valid ways I can do that. I might indicate the polarity. This is the higher polarity side. Voltage is 50 volts. Or if you prefer, change the polarity and then designate that as a negative 50 volts. Again, equally valid either way. Now, for whatever reason, I'm convinced that students look at a negative sign and assume they've done something wrong. And that's something I've got to break you of if that's kind of the belief you have at this point. Then the final two electrical quantities, power and energy. So power is the rate of energy transfer. And if you notice in the context of what we've just defined, when we're talking about power associated with an electrical element, it is the voltage across that element times the current flowing through that element. So in the future, anytime I ask the question, what's the power associated with an element, all you need to do is multiply V and I together. Again, I'm assuming this is all review that units joule per second, or more commonly called a watt. So I imagine you anticipated this was coming. If we have to worry about direction and magnitude for current, polarity and magnitude for voltage, we're going to have to adopt some kind of sign convention for power. The one the textbook uses and the one I'll use as well is what's called the passive sign convention. Now initially this may seem a little bit clumsy to you, but trust me, once you get proficient, you'll understand why we put so much emphasis on this sign convention. All right, a question for you. From a power perspective and from a circuit perspective, what two types of elements are there? Again, from a power perspective, if you were going to classify in a circuit, what are the two types of elements you would see? Okay, so resistive is an example, like lighting is resistive, so it's a load. It's something that is taking energy from the system. So yeah, that's certainly a good example of one category. That would be a load. What would be the second? Absolutely. So a source is the second type. You have to have generators or something in the system that are actually producing that electrical energy. So we're going to take that perspective as we describe this convention. So a passive element is what we recognize as a load on the system. Here's the criteria that you need to be watching for as it pertains to a passive element. Passive element, the current is going to be flowing into the positive terminal as it pertains to the voltage. With passive sign convention, we then calculate the power as V times I as we described. And then just want to emphasize the interpretation, the power dissipated So the power dissipated by a passive element is positive. So that's the first half of the sign convention. Okay, so sources are described as active elements. And what you'll observe is, for an active element, the current now, instead of entering the positive terminal, it leaves the positive terminal. And we will compute power as negative V times I. And then some wording to go along with that. The power dissipated by an active element is a negative quantity. Yes, sir? Yeah, and that's an excellent question for everybody to ponder. So the question, what is meant by, in the latter case, power dissipated by an active element is a negative quantity? What's that another way of saying? Absolutely. And it may seem clumsy at first glance, but as we develop these systematic methods of circuit analysis, if you give it time, you'll see why that's such an advantage to have that. But yeah, this is simply saying that an active element is providing energy to the system. But we will use or rely heavily on this passive sign convention. Any other questions on that? On the time remaining, just want to briefly address some terminology. And again, you'll see as the semester evolves why having an understanding about some terminology that we'll discuss is going to be so important. So let me just start by defining a circuit. A circuit is simply an interconnection of circuit elements. So let's just take a hypothetical case. And then certainly something you determined or utilized in your Physics 2 experience. For the time being, how are we going to treat the wires that we use to interconnect the circuit elements? In other words, should we worry about some incremental resistance those wires have? No. For starting, we will treat the wires as perfect conductors, and we won't worry about that. Now, on the other hand, if you're looking at a power system where we've got a 100-mile transmission link, do you think you can ignore the resistance there? No. So you always have to change your model based on the situation. But certainly as we start this process, we won't have to worry about the wires. So here's a simple circuit. A little later on in the course, we're going to develop what's called the node voltage method. It's by far the most powerful circuit analysis technique that we'll ever present. So you better know what a node is, otherwise you're going to be right off the start having trouble with the node method. So a node is described as a point where two or more elements join. I'll wait till a little bit later. But But the textbook does make the distinction between what's called an essential node and a non-essential node, but for now, a node is just a point where two or more elements join. How many nodes are in my example? Okay, so 2, everybody agree with that? All right, so let's identify the nodes. So that's certainly a node there. So there's a node there. And then these are easy to miss. That's also, based on our definition, a node. So there are 3 nodes in this example. Everybody clear on why those 3 points represent the nodes in the circuit? All right, next, let's discuss a loop. So imagine from Physics 2, most of you have a little more experience with the concept of a loop than maybe you do with a node. So a loop is simply any closed path in the circuit. So how many loops do you see in this circuit? Yep, so 3 is correct. So we've got loop there, loop there. So again, any closed path, as long as where you start, you return to, that designates a loop. And then finally, the other topic I'd like to mention is the concept of a mesh. We will also develop what's called mesh current analysis, an equally powerful circuit analysis technique. So it's important that you recognize how to identify meshes. I guess there's really no clean way to describe this. So for lack of a better definition, I would describe a mesh as a loop not containing other loops. Another perspective, you could view that as panes of glass in a window. The various panes would represent where the meshes are going to be flowing. So in this example, how many meshes are there? Yeah, just 2. And as you may recall from Kirchhoff's laws, that you certainly spent a lot of time on in Physics 2, if we're dealing with Kirchhoff's current law, our focus is going to be on nodes. If we're dealing with Kirchhoff's voltage law, our focus is on loops in the circuit. Okay, so KCL, Kirchhoff's current law, is really nothing more than the statement of the conservation of charge. A nice, clean way to summarize KCL is to indicate if you sum the currents at any node, the net current entering a node must equal 0. So again, conservation of charge. Second law then, KVL, or Kirchhoff's voltage law. That is a statement of the conservation of energy. So a nice way to represent that is to essentially pick any loop, any closed path in the circuit, and simply state that the algebraic sum of the voltages around any closed path must equal 0. Now you can, and this may seem like I'm overstating things, but essentially everything we do in this class from this point on is going to be based on those two laws. So I just want to get you thinking in advance. If you see anything that violates those two fundamental cornerstones of physics, then you should become suspicious that even though it's drawn on a page in a textbook or up on the board, probably can't exist or definitely can't exist, and that's going to help you understand when they begin to ask you, is this a valid interconnection, what the perspective will be. So this is a good place to stop for today. Any questions before we conclude? All right, see you on Friday.